Yeah, Prashant.
AI class is now itself for them. No, sir.
Hello.
Hello.
Yeah, yes, Prashant.
AI class.
Hello.
Hello. Can you hear me, sir?
No. AI, right?
Yes, sir.
Just a minute. Let me check.
Sure.
I think, yeah, let me check one more. Okay.
You are currently the only person in this conference.
Hello, Swapna. Can you hear me? Yeah, fine. Okay. So the two of you are here right now. That's fine. But let's wait a couple of minutes, then we'll start. Well, until then, maybe you guys can tell a little bit about yourselves. You guys are both from computer science background. We take in CS, Shreya and Swapna. And you're both what, final year students, pre-final year or working? Okay, both of you are from final year. Fine. And which college are you guys from? Okay, New Horizon. Okay, SDIT Bangalore. That's good. You're in final year there, Swapna. Okay. I had visited SDIT, I think, last month for a gate jam outreach from IIC. Did you have an outreach session from IIC students, Swapna? Or were you not there? You were there, okay. Oh, nice. That's good. Fine. I think it's going to be just the two of you. It's okay. So one more thing I need from you guys. What all the subjects have been covered from the DA syllabus. There's probability, statistics, linear algebra, calculus. Machine learning is still going on. Okay. And everything else, it has been covered. Okay, fine. Okay, then let's start with today's session. I'll start off by introducing the syllabus just a little bit. Syllabus for AI, that is. There's essentially 3 sections. First one is search algorithms. There's informed. Informed and adversarial. And there's logic in AI part. This thing, it overlaps with CSA also. Propositional and predicate logic. Right. The final one is reasoning under uncertainty. This is what's mentioned in the syllabus. I'll be covering a few things other than this also. First, there's conditional independence representation. Exact inference through variable elimination. Hello? One more person has joined. 2 more people. Fine. That's good. The last one is approximate inference through sampling. This is what's mentioned in the syllabus. Seeing this, we can easily tell that it's not fully clear. So I'll be covering additional topics as needed. Fine. So today, rather than starting off with search directly, I'll start off with something much more fundamental, logic. Okay. So this propositional and predicate logic, have you guys heard of these things before? These are part of GIT CS syllabus also. You must have studied it over there. Fine. So okay, then let me start off with this topic. I won't stick to just these two. I'll cover a few other things other than this. So let's start with this topic. What is logic? On the formal definition also, in your own words, can you guys tell what it means? I would say that it's the study of reasoning. Okay. So what happens inside this? We start off with some premises. Okay, and from these premises, what do we get to? I'm audible to you guys, right? Yeah, then please answer. Answer what you know. Start off with the premises and to get to what? To get to some conclusion. Okay. And in logic, there are two types. The first one is formal logic. This is also called as symbolic logic. Also call it mathematical logic. Okay. So in formal logic, what all will be there? This one it examines the logical form. And it is independent of the concrete context. Okay. And this independence, it is to be topic neutral. Right? Another property of this is it has deductively valid arguments. And for this, we have certain rules. They are called rules of inference. Okay. Other than that, it has logical truths. Logical truths meaning what? These are two true statements under whatever interpretation we have. Other than that, sorry, it uses formal language also. Meaning the vocabulary is limited and the syntax is really exact. Okay. This was regarding the first type, formal logic. Second type, there's informal logic. Okay. So this one, it uses non-formal criteria. For assessing the correctness. Okay. The whole point of this informal logic is it is to bridge the gap. It is the gap between formal logic and natural language arguments. Fine. Any doubts till here? We'll take one example. So let's say the argument is birds fly, Tweety is a bird, therefore Tweety flies. Formal logic, I will write this. I'll write for all x, okay. In formal notation, it will look like this. Are you guys familiar with this kind of notation? Okay. Okay, since you guys are familiar, I think we can interact and just get the class over with. It doesn't have to be one way, the communication. Going ahead, coming to natural language arguments. So what issues do they have? They can be ambiguous, be vague, they can be context dependent also. Okay. Another phrase I can use for them is they are non-reductive arguments, meaning that the conclusions they are probable but do not ensure the truth. Example, I can take an empirical observation. Let me take all ribbons I have seen so far are black. From this, if I get to the conclusion, all ribbons are black, this statement is probably true, but we are not 100% sure. Other than that, this logic also involves a study of informal fallacies. Okay. So what is this fallacy? What do I mean by this? I need you guys to answer this. Not sure. I mean, it's an English word. What do you think it means? Sapna? Neha? Pradeep? What do you mean by fallacy? It's not a logic question also, just a simple English question. Can you give an example of a fallacy? Fine. Fallacy is a type of incorrect argument. Essentially, these are errors due to the content and the context, the argument. For example, false dichotomy, false dilemma. Have you heard of this false dichotomy or false dilemma fallacy? Not heard. Okay. Fine. This fallacy happens when in your argument you exclude viable options. Okay. So, for example, if I take you are either with us or against us. So from this statement, going ahead with you are not with us. So what conclusion can I draw from this? What conclusion can I draw from this? Making a statement, you are either with us or against us. If you are not with us, then you are against us. You're getting the context, right? Think of this like a discussion between two people. So this is essentially a false dichotomy. Can you tell me why? Because there's only two choices, with or against. What other valid choices can be there? Think of something, Assume you're having an argument with your friend. Your friend says this, you're either with me or against me. Since you're not with me, you are against me. What would be a fitting reply to that, logically? Another option is, you don't care whether you're associated or not. Okay. So the person saying this, whatever issue they are having, that issue is irrelevant to me. So one really viable option is don't care. Is it clear, the point that I'm trying to make? Fine. Go ahead. Let's go to some of the basic concepts. I mentioned one word before, premises. What do I mean by premises? Premise is essentially a declarative statement, also called as a proposition. Okay. So proposition is essentially a true or false declarative statement. Next, there's conclusion. Conclusion is also a proposition. And in the beginning, I mentioned that the premises, they are used to prove the truth of conclusions. Okay. I've just started the theory right now. The beginning, I think it will be really boring because all these basic words I'm introducing. So please bear with me. What is an argument? It's a set of premises and a conclusion. Okay. And if the argument is meaningful, what's the meaning of this? What's the prerequisite for this? For a meaningful argument, it requires that all the premises they should be true. Fine. Then logical consequence. It's also called as entailment or an implication. So this one, it describes the relationship between statements that hold true when one statement follows from one or more statements. Then what is a valid logical argument? The argument is a set of premises and a conclusion, and that will be valid if the conclusion entails the premise. Okay, entails meaning follows. Right? So these are separate things. Having all premises as true then having the conclusion follow the premise, we have to account for it separately. And logical truth, for example, either Mars is red, Mars the planet, or Mars is not red. Is this statement true or false? I'm making this statement, either Mars is red or Mars is not red. Yes. This true, that to always. And what do we call a statement which is always true? A proposition which is always true. What do we call it? Yes, we call it a tautology. Have you heard of this word, tautology? Yeah. What is the opposite of this? The opposite of tautology. Tautology is a statement, is a proposition which is always true. A proposition which is always false. What do we call that? No one. It's called a contradiction. This is always false. Fine. Did you guys know about this word, contradiction? If you answer these questions when I ask, you can quickly move forward. Otherwise, I won't really know how will you know this subject. And moving ahead, let's look at what inference means. Inference is the steps in reasoning. So there is mainly two types of inference. First one is deduction. Okay. What does deduction do? It derives the logical conclusions from the premises. Okay. These premises we either know or they are assumed to be true. Another type of inference is induction. So this is inference from a particular evidence to a universal conclusion. Okay. Other than this, there is one more type of reasoning. It's called inductive reasoning. Okay. This is essentially the simplest and most likely conclusion from a set of observations. However, this has one drawback. It does not eliminate uncertainty. Okay. Regarding the simplest and most likely conclusion, there's a phrase for this: Occam's razor. Have you heard of this, Occam's razor? You should look into it. It's not like it's 100% into logic. The principle is the same. The simplest and the most likely conclusion, that's usually the right one. Okay. But then there's fallacy. Already mentioned this. It's essentially an incorrect inference. Okay. It is faulty reasoning. So why these fallacies happen? Foremost one is intentional. Okay. The idea is to manipulate or to persuade someone. Can be unintentional also. Okay. This is due to carelessness, or maybe due to bias. It can also be due to limitations. Limitations of language or understanding. We'll take an example of a fallacy. Coriscus is different from Socrates. This Coriscus and Socrates both are Greek people. Socrates was a great Greek philosopher. So this logic actually has roots from Greek civilization. So that's why these examples that I'm going to give, they usually have these Greek names. Fine. So the first proposition I have is Coriscus is different from Socrates. And statement that I'll make is Socrates is a man so what conclusion can I draw from both of this? I'll go ahead and draw this conclusion. Therefore, this Coriscus is different from a man. Okay. Is the statement true or false? Is it logically following the previous two statements? Guys, please answer. No, it's not actually following. This is a fallacy. Okay. This does not actually follow. Is it clear why this is a fallacy? I mean, it's not about having to prove it. Just with your common sense, you should be able to tell. I mean, I can take an example from whoever is there in the class now. Your Shreya and Swapna are there. I can say Shreya is different from Swapna. Shreya is a woman. Therefore, coming to the conclusion that Swapna is different from a woman, that is wrong. Okay. Why exactly this is wrong, we'll come to that. This is just the first class. However, using your common sense, you can spot some fallacies. That's the point I'm trying to make. Okay. Fine. Moving ahead, the next concept, it's of a truth table. So this one, it shows how logical connective works. And why do we use this? We use this to analyze the truth values of complex propositions. I'm sure you guys have seen truth tables before. I'm not from computer science, but these truth tables I've usually seen when it comes to digital electronics. So there's usually one column for each input variable. And each row corresponds to one combination of inputs. Okay. And the truth values, they're either true or false. Or we can also write this as 1 or 0. As I mentioned, digitally. Okay. Let's look at a brief history of logic now. So, systems of logic. So, this was developed back in Greece. That's what I mentioned. So at that time, what was developed, it was called Aristotelian logic. As we progressed, we moved into the modern era, where we have classical logic, extended logic, and deviant logic. Okay. Coming to Aristotelian one. It's also called as term logic or syllogistics. Okay. So there's this word here, syllogism. Okay. It's essentially an argument only, specific type of argument. Argument with 3 propositions. So these 2 of these propositions, they are going to be premises, and one is going to be a conclusion. Okay. This can be valid or invalid. Right. Now, coming to the propositions, each proposition, it has 3 parts. Being very specific with what I'm telling here. So if it's not fully clicking, it's fine. This is just for proper background as to how logic came. We'll have the subject, the predicate, as well as the copula. This copula is what connects the subject to the predicate. Okay. The properties of this Aristotelian logic was that it had only simple propositions. Okay. And the subject should be categorized into 4 types. First one is universal, second one is particular, then there's indefinite and singular. Okay. And you guys have done problems on Venn diagrams, right? Logical problems, that is, all knights are knaves, all this are that, some this are that. Correct? Actually, it is stemming from this logic only. Universal, from name only you can say, for example, let's say humans. I'll say all humans. Okay, all humans in the universe, that will be the universal subject. If I want some particular form of the subject, I'll replace all with some. Okay. And indefinite, it will look like a human. And for singular, I'll have to be very specific. Usually humans, they have names, so I'll go with a name, Socrates. Okay. Are these 4 types clear? Okay. let's take some examples. I'll say all men are mortal. And Socrates is a man. Therefore, Socrates is mortal. Is this valid or not? This entire argument, this entire syllogism? Yeah, this one is valid. Using your common sense, you're able to tell it. And yeah. All cats are mortal. Previously, I proved that Socrates is mortal. Therefore, Socrates is a cat. Is this valid or invalid? Answer with common sense, not with strict proof. Yeah. Clearly, this is invalid. And could you tell me what's the fault in this logic? You can obviously see it, but in the system of formal logic, we need to have certain proof. Yeah. If I try to draw it, I think that will make more sense. Set of all mortals. I say all men are mortal, so men will come inside here. And inside the set of men, Socrates is there. Okay. So this logic will be valid. And if I say all cats are mortal, then I'll take all cats inside this. Okay. So it's not necessary that Socrates, he has to come from inside this. Socrates can come from outside here also. Okay. Okay. Okay, then let's move ahead. Next topic I'll take is the square of opposition. Okay. So this represents the relationship between the four basic categorical propositions. Okay. And The relationship can be that it can assert, it can deny everything, or it can assert some, or it can deny some. Coming to the categorical propositions, I'll list them now. We can have all, can either have it as an universal affirmative or a universal negative. And some can be a particular affirmative or particular negative. Okay. This assertion and denying of all or some, I'm talking about members of one category being included in another. Okay. Fine. I'll start drawing it. Before that, one more thing I need to mention. S, I mean it's a subject. P means a predicate. It's just notation that I'm going to use. Okay. So let me draw this square now. Fine. So here I'll make a statement. All S are P. All subjects are the predicates. Okay. In other words, I can write this as SAP. So this universal, I think I should mention that also. I'll just use the smaller letters over here. So that to not confuse between the subject and predicate. And with this, these are entities and these are actions. I will be I and O will be small o. All SRP, so S and P. Fine. So how can I mark this? All SRP, it corresponds to this one. And this part is empty. Fine. Is it clear what I have marked? It is this one. And it's A because it is universal. Yes. So contrary to this, you can have no SSP. Okay. Same sets. Where should I mark the red? Red area. Which area is going to be empty in this? I need you guys to answer this. I want to know if you're following this or not. Think of this like an aptitude question only. Which area is empty here in this? I'm saying a statement that no SSP, then which area should be red? Let me mark the three areas, X, Y, and Z. Should I mark X as red, Y as red, Z as red, or multiples, X and Y and Z? What should I mark as red? I'm audible, right? Yeah. The empty space is the intersection part, which means that all elements of the set S, they lie over here. Okay. So this I can also write it as SEP, the universal negative. All elements of S are not in P. Here all elements are in P. Here all elements of S are not in P. So this is called a contrary. Right? And over here I can write hold on, make some more space. I can write some SRP. Or SI. I meaning particular affirmative. Affirmative meaning it is positive, some are there, nothing is being negated, and some of them are there. The same two sets, S and P. So any red area is there? Which area should I mark as red? In same X, Y, Z. Which area is red here? Yeah, they may or may not be empty. So which area should you mark as red? Y must be non-empty. And what about empty? Which one is empty? We can't say. So all elements of S, they don't really have any restriction. They can go wherever they want. Okay, so no area is going to be marked red. The final one, sum S or not P. Okay. So this one will also be same one, same area, but the difference is sum S are P, I'm referring to the intersection. Sum S are not P, I'm referring to the ones that are not inside. Okay. This is SOP, a particular negative. Fine. Is it clear the distinction between all four categories? One is universal. Universal ones are at the top. The particular ones are at the bottom. And on the left, the affirmative ones are there, right? The negative ones. I also mentioned that these two are contrary. These two, they are not strict, right? This contrary part, it is really strict, either here or here. But here, the overlap is allowed. So we cannot have the same word. So we use this word of contrary. Okay. They are opposite to each other, but in a soft manner, I'd say. Okay. Other than that, the universal to the particular. I have subordination. Just move everything. What is the subordination? Means that the particular is implied by the universal. If all S are P, then obviously I'm going to find some S which are P. Right? All S, they are going to, I can find it in the intersection. So some of these they are going to be belonging to S, right? It's an obvious piece of logic, but still we need to, since we are studying logic, we need to define it properly. Is it clear what I mean by subordination? We can take over here also. No S is P. In the intersection, nothing is there, everything is outside. But over here, some S are not P. So they are outside. On the inside thing, we don't really care about this fourth case. Right? Yeah, so the square of opposition. The opposition is not fully clear. I'll draw that now. I'll draw the ones which are contradictory. All four are contradictory. If I take one diagonal, all S are P, and some S are not P, we can't really draw any logical conclusion between them. Okay. Then between these two. No S is P and some S are P, we can't really guarantee where any element lies. Right? Okay then. That much is enough regarding Aristotelian logic. The whole point was to give a general idea as to the kind of things that were addressed. And from there, we move ahead and build upon classical logic. So this one, it encompasses propositional and first order logic. What is another name for first order logic? Yeah, another name for first order logic is predicate logic. There are other names also. See them one by one. In classical logic, is based on logical intuitions. Like, can have the law of excluded middle. What is this? I can take A union with the negation of A. What will this give me? If I take a set and the union of its negation, then what will be the result from set theory? A union A dash, what is it? Yeah, universal set. And the universal set, I can consider it to be true always. 2 slides ago, I used an example of this, right? Yeah, either Mars is red or Mars is not red. this proposition A will be Mars is red, the negation is Mars is not red. I'm taking or disjunction. This is going to be always true. So essentially this statement was an example of this law of the excluded middle. Another example I can give is double negation elimination. Fine. So for this, what can I write? You can take A dash, the whole dash. What is this going to be? I'll be getting back A. So this law is called the double negation elimination. And here there's one more principle, the bivalence of truth. Meaning the truth values are true or false, nothing more. Thing is, because of this bivalence, this becomes a little limited. Sometimes the truth, it can be a little fluid depending on the context. So having more values than just two, maybe having an entire spectrum also, that makes sense. Okay. Other type of logic, it's extended logic. So here we accept the basic principles and then we introduce additional symbols. So inside this one category is modal logic. Okay. This one, it introduces two new symbols. These are the two symbols. The rhombus, it means that something is possible. The square represents something is necessary. Fine. So from this, we can get some new inference rules. Okay. From these new constructs, we can get if something is necessary, then it is also possible. Fine. Is this rule making sense? If something is impossible, then it probably isn't necessary, right? I'll write one more inference rule. If something is necessary, then its negation is impossible. Because of these two new symbols, something being possible and something being necessary, we can get inference rules. There's some other forms of modal logic also. One is deontic. This one deals with ethics. So this has ideas like obligation and permission. Then there's temporal modal logic. So this has ideas like something happening at one time, things happening at all the time, those kind of ideas. Like something. Kind of things. This stands for something. Can have epistemic logic also. This has ideas like knowing versus merely believing. Okay. And is it somewhat clear? This categorization that I'm giving. These things, they turn philosophical real fast. But at least as students preparing for GATE, you should at least know that these kind of things, they exist. Okay. And moving ahead, let's go into higher order logic. This one, it introduces new forms of quantification. This quantification, it is introduced when it comes to predicates, right? Predicate logic. Before that, in proposition, there is no quantification. So that quantification, the freedom that we have, that increases. This one, it increases. The thing is that this one, it has drawbacks. Okay, the exact drawbacks I won't go into, and because of this, we prefer first order logic only. Okay, So when I say it increases, okay, let me be more clear. It increases the expressive power. Moving ahead, next we can have deviant logic. This one, it rejects some intuitions of classical logic. So we can see this as a rival to classical logic. Inside this, we can have some properties. So I'll say it is intuitionistic logic. Okay. This one, it excludes some inference rules. Okay. For example, the double negation thing. Negation of negation A is equivalent to A. Is that right? When we come to deviant logic, this need not be true. Okay. At least some example, we can set up a universe where this doesn't hold. Other than that, there can be multi-valued logic. So this one, it rejects bivalence. Okay. So bivalence, I mentioned it is either true or false. We can have additional values. Okay. Can you give me some example for this multi-valued logic? Can go to digital electronics here. You have digital electronics in your computer science syllabus, right? Yeah. So in that, a variable, what all values can it have? 0 or 1? Other than that, other than 0 and 1, what can we do? What other values can we assign to a variable? We can have things like indeterminate. We can have don't care. Okay. Karma marks, we see this, right? The don't care. So with don't care, we're taking the first step out of this bivalence. When we do karma maps, trying to get the expression, some values, it doesn't really matter if it's 0 or 1, even if it's something else, it's fine. Other than this, there is para-consistent logic. This one, it deals with contradictions. A very popular way of proving a few statements is proof by contradiction, right? Sometimes the degree to which the contradiction is there, that will vary also. But is to analyze that, we need to have certain branches. That's where this para-consistent logic comes. So this one, it avoids the principle of explosion. What is this principle of explosion? It states that from a contradiction, anything will follow. For example, let's say regarding this principle of explosion I'm talking about now, you can say it is raining and it is not raining. Clearly, this is a contradiction. Both of them, they cannot be true at the same time. But if I assume this to be true, then I can logically prove anything. Okay. Let me give a little bit more about this para-consistent logic. Why, how can there things like this even come? So this motivation for this. So that is dialtheism. That is the view that statements are both true or false. True and false, sorry. Okay. Let me take an example and give the liar's paradox. Okay. The statement is very simple. A person who is a liar, he declares, I am lying. Have you heard of this liar paradox before? I remember back when I was in school, maybe even 11th, 12th, we used to discuss things like this, but we didn't really know how to analyze it. Now, these things, they actually have a lot of basis. Have you heard of this liar paradox before? Okay. can you analyze this? This person, liar, I'll call A. Is he telling the truth or is he lying when he is making the statement? Which one is correct? Or if you can't answer this question, how will you manage the scenario? Neha, Swapna? Have you seen this before? Okay. Fine, then try to analyze this. We have a liar A. He's declaring that he is lying. He declares I am lying. So is he telling the truth or is he lying? Can you analyze this or not? Is my question clear to you? What I'm asking of you? Yeah. Then, I mean, a definite answer is probably not possible here, but still, what analysis can you do for this? Okay, fine. Let me try a little bit of analysis. Let me assume that he's lying. Okay, so he's declaring that he's lying, and this is a lie. This means that he is telling the truth. Okay, but we know that he's a liar, so he must be lying. Okay, and if I assume that he's telling the truth, then he must be telling a lie. Okay, which means that it's again going to imply the truth. So point is, there's a circle. We can't really figure out what the status is. Okay, so this was more of a riddle kind of thing. In a more formal setup, we have things like Russell's paradox. Since I am mentioning this paraconsistent logic, all these paradoxes are going to come. Right? So what is a paradox? I think at least this you can answer. What do I mean by a paradox? The English word paradox. Yeah, so contradiction. But when it comes to contradiction, this means something which is always false also, right? So yeah, but the English word contradiction, it makes sense. I mean, not write it this way. Paradox means it's a contradiction. And simply write, it's unclear what the output is. Russell's paradox. Have you guys heard of this? Okay. This one was one of the most important breakthroughs in set theory. I'm going to define a set R. Okay. It has elements X such that X, it does not belong to R. Okay. Is the definition clear? R is a set which has elements which don't belong to them. Right? So what elements does R have? What are the elements of R? Does it have numbers? If I analyze this, I can get that R, it should belong to R, should be subset of it. This means that if in place of X, if I put R, I'll be getting R does not belong to R. Okay, so we'll be reaching a paradoxical state. The output we cannot get, but at least the situation you can understand. So historically speaking, when maths was under development, specifically set theory, this person Russell, he came up with this argument, and people had to come up with new rules to manage set theory. This thing, I think, is what gave us ZF, set theory, Zermelo-Fraenkel. The whole point was to avoid situations like this. Okay. Moving ahead, let me go to the next topic. The whole point of introducing these things was to give the importance of all these various branches. When I started explaining parallel consistent logic, maybe you guys thought we need to deal with contradictions. Things are usually clear. But these examples, they are telling us that things are not clear. First one is just a riddle. The second one, this was shaking the foundations of math. Okay. Moving ahead, let's look into informal logic. So this informal logic is what we use on a day-to-day basis. This is more pragmatic. Pragmatic meaning practical, or a dialogical approach. Okay. So this is usually a speech act, a conversation between two people, and the context also matters. So what is true in one context may not be true in another. Okay. So we can treat this as a game. Okay, so with initial position and premises. Fine. sidestep and ask one question. Have you guys studied game theory? Not at all. Have you heard of this at least? What the setup is like? Yeah. And that much is enough, I think. So when I say game, you should not think of childhood games and game theory kind of games, which actually includes childhood games also, but formula analysis of the same. Right? And other than this, in this pragmatic one, there is persuasion. And the arguments, they correspond to the moves that we make in a game. So two people are there. One person presents his argument, a counter argument will follow, the cross questioning, so back and forth, essentially a game. Okay. So this is the first one. Second one. Second one then is epistemic approach. Okay. So the idea behind this is that arguments, they increase the knowledge. Okay. So if we have correct arguments, it will expand the knowledge. And if we have fallacies, they give us failures. Okay. For example, we can have something like begging the question. Have you heard of this phrase, begging the question? You haven't heard of this phrase in English I'm talking. Okay. The fallacy of this begging the question, it essentially assumes the truth of the conclusion. I'll try to give an example for this. For example, I can say wool sweaters are better than nylon jackets. Okay, this is the claim that I make, and the reason that I give, because wool sweaters, they have higher wool content. Okay, which is a fallacy only. Thing is, it is referencing the argument's conclusion. It is assumed in its premise. Right? So regarding this epistemic approach, Given example is a Bayesian approach. So in this category, the degree of the belief matters. Okay. This degree is called the credence. So if you get new info, then the credence will change. The degree of belief, it will change. Okay. I think I'll stop here. I'll mention a few small things also. All these things, they are fairly funny, whatever I mentioned. Yeah, however, they are of high importance also. There are a lot of areas of research where these are applied. There's philosophical logic, then meta logic. So this one, it studies the properties of logical systems. Then mathematical logic also I mentioned. Then there's computational logic. Okay, so essentially using computers, how we will implement logic. So for example, we can have automatic theorem provers. Boolean logic also. And other than that, that's formal semantics of natural language. And I think this last one is the main reason why we are studying logic as part of AI. There's natural language processing, a major part of artificial intelligence. So understanding the semantics, so that we need logic. Okay. Okay, then I'll stop here then. The next class I'll start off with propositional logic. Fine. Okay then. Thank you guys for your time. I'll see you in the next class.